Hi folks, welcome back. We're in the calculus zone. We just previously looked at the basic rules of integration for certain mathematical functions. You like to call them equations, but whatever. So we're going to look at an application now. So we're going to look at something known as area between curves. So to give you a really basic example here, area between curves, you could look at two horizontal lines, two vertical lines that all intersect, and that would give you something called a rectangle. And you know, well, hopefully for a rectangle, it's length times breadth. But sometimes it's not always, you don't have such things that are as simple as straight lines. So you might have something like this. So the red kind of hatched area here, shaded area, that's the area of interest. So we've got kind of two boundaries here. Between x equals a and x equals b, from extreme left to extreme right. And I'm referring to those kind of curvy boundaries as y equals g of x and y equals f of x. So that's just the name of the curves. Right? They're just dependent on x, like x squared minus 5x plus 6, whatever it is. So we're interested in that red zone there. So how do we use this integration without going back to this thing called first principles, i.e. the person who sorted it out in the first place? So what we're going to do, so the things that we're interested in is extreme left, value of x, which is a, we'll have a number x equals b, extreme right, and the uppermost curve, which happens to be f in this case, and the lowermost curve happens to be g if you follow the track of it. And the way we calculate this is, you've seen this summation symbol, sometimes we call it the integral sign, whatever. We all get confused just like you do. So what we're interested in here, we're going to sum up really from bottom left A up to top right B. So what I'm talking about here, on the left, x equals a on the horizontal line to x equals b. So that's furthest left and furthest right of the area. So we're trying to encapsulate the area here. And so we actually need to encapsulate top and bottom. So that's what we've done there. Okay. So there you go. We'll get rid of everything else. So I'm just trying to emphasize here. I know this looks like a pair of lips, right? So that's the top curve in blue. I'm coming down from the top, and the one coming up from the bottom in green, that is a bottom curve. So we're going to have equations for these, or function names. So there you go again. So area is the integral from a to b. So that could be like 7 to 19. Top curve minus bottom curve. The wee dx just means everything involves dx for us here in relation to x with respect to x. So putting in the two names of the curves, f of x, g of x, f and g, we're just going to have, we can just put f and g, or just the function names. Forget about the wee dx, it's just, these are all in there for technical reasons. So here we go. Why don't we just fire right in there with an example? So we want the area bounded or surrounded by the two curves, which are the function names y equals 4x minus x squared and y equals x. So you may recognise that the top one is a quadratic function and the bottom one is a straight line. So, but that doesn't matter really. But sometimes they give you a wee graph to give you a wee hint what you're looking for here. So the straight line is the y equals x, and the curvy part is the 4x take away x squared. And it hatched in blue is the area of interest. So going through this, so what we need the extreme points of contact, extreme left point of contact and extreme right point of contact. So these are called the limits of integration. So they're saying equate the curves there. So equating the curves here means it's a 4x take away x squared and the x. So where they meet, the x values and the y values will be equivalent. So that's what we're going to do. We're going to take them, y equals x and y equals 4x take away x squared, and we're equating them. Okay, we can get rid of the y because they're equivalent on those points. So here we go. Just get everything over to the one side. That's what we've done there. You've done all this stuff before, folks, so we don't have to go over the history of mathematics. Looks like we've got a quadratic on the left-hand side, and it looks like we've got a common factor of x. I think I'm just going to factorise this here. Done it. Okay, so now I'm going to separate and solve. So I'm going to have x, which was a common factor. I'm going to set it equal to 0 in the contents of the bracket. X take away 3, I'm going to set that equal to 0. So there you've done. So the one on the left, x equals 0, that's solved. And x take away 3 equals 0. I just need to solve that for x. So we're going to isolate that 3, just chug it to the other side, or technically add 3 to both sides. So there you go, but we're two solutions or one limits of integration. X equals 3, x equals 0, and x equals 3. Right. So I've got my little formula here. Area equals top take away bottom. Top and bottom are the curves. Graphically, I put in my limits of 0 to 3. Okay, so numerically, you put the lower one in the bottom, the greater one in the top, so 0 to 3. So top minus bottom. So what was the top curve? Well, it was 4x take away x squared. The bottom one was y equals x. So I'm just going to fire back here to show you that. So the curvy one, can see how that is a top boundary. That was a 4x take away x squared. And the lower boundary was a straight line, which is y equals x. So top minus bottom, so that's why it was in that order there. You saw a bit flicking about, folks. So that's why we'll get that. I've put in these brackets for a reason. It's to keep things safe. The first one is going to be fine. There's nothing in front of that first bracket I need to multiply other than 1. But the second bracket, you've technically got a net. That minus turns into a -1 now. So -1 times x is -x. So that's what I've done there. Now I'm going to gather like terms. So I've got two kind of x terms. I've got 4x, then I've got a -x. So it'll become 4x take away x to give me 3x. And then -x squared stays on its own. So that's what I've got there. And so I'm just coming down the page here. So what's going to happen next? We're going to integrate here. So 3 to x to the power 1. So 3x to the power 1, that goes up to, we're going to increase x to the power 1 to x to the power 2 and divide by that new power. And the x squared, that 2 goes up to 3 and divide by the new power. That's what we've done there. And what I've done, I've moved these things called limits, the 0 and 3 on a summation symbol or integration sign, if you want to call it that. I've moved them to extreme right. It doesn't matter as long as we're aware what they are. And so now the result here, 3x squared over 2, take away x squared over 3, that's what I'm going to use to help us evaluate the area. So I've got two limits here, 3 in the top, 0 in the bottom. The top one always goes in first to what you've got in the box here. And we automatically subtract the same thing, but with 0 in place of x. So that's what we're going to go for next. So I've just taken it on to the next page. So can you see that there? I'll just go back. What's in the rectangle there? I'm reproducing that twice. I'll get rid of x because I'm going to put in the limits, the 3 in the first one and 0 in the second one. There. So in the first one, we're going to put 3. In the second one, we're going to put 0 everywhere x has appeared. See that there? So we're just going to do a little bit of arithmetic here. So 3 times 3 squared. 3 squared is 9. 3 times 3, 9 is 27. So I'm going to have 27 over 2. Moving along the line, 3 cubed is 27. 27 over 3 is 9. So what we're going to have there, so I'm going to have 27 over 2, take away 9. That's fine. And see that second bracket, it'll all come out to 0, believe me. So just going down, after we're done with arithmetic, get that there. Your calculator could do it all in one go. That's fine. 27 over 2, take away 9. That's like saying 27 over 2, take away 18 over 2. Having a common denominator. So I'm going to have 9 over 2, take away 0. Remember about that second bracket there. I'm just bringing it down just to be consistent here. And that will just give you 9 over 2. Some of you will like to write that as 4.5. It depends what the scenario is here. What's the story? Why do you need this answer? Some of you might want to even decimalise it. That's fine. So we've got that there. I'm sure all those answers are acceptable, but like I said, dependent on the context. Right, so that's our first one there. Oh, and remember, our scenario here, we were talking about an area, so I put in units squared. But please, folks, integration doesn't always refer to area. It can refer to loads of topics. We're just using area initially, because that was one of the first reasons it was used for, or developed for. Right, okay, let's move on. So what we're going to look at here is basically the same type of scenario. Hopefully you know the top one, y equals 2x, is a line. The bottom one looks like a quadratic, which is represented by a parabola. So I'm going to give you a wee picture here. And there you go. That's not too bad, Tommy boy. And so what we're interested in here is where the line and the curve actually meet. So what we're going to do is find these limits of integration. So we need the extreme left-hand side of the area and extreme right-hand side of the area in terms of the x value. So that's what we call the limits of integration. So if we take those two curves, 2x and x, we'll take away 6x, and we just make them equal to each other, it doesn't matter which one goes in which side. But you'll learn just by practice which one you should put in the left, which one you should put in the right, try and avoid negatives. So we'll get everything over the left hand side because we want to make it equal to 0 in order that we can solve an equation. So it looks like I can factorise this, common factor of x, just like the last one, take it out, x to the front bracket, x take away 8 close bracket equals 0. We've got that there. So now we'll get something times something equals 0. So we're going to separate and solve. So we're going to have x equals 0 or x take away 8 equals 0. Left hand side is done, x equals 0. On the right hand side, x take away 8 equals 0. Just let that 8 jump over the equal sign and we'll isolate x and hopefully we'll solve it. So that's for two limits of integration, the extreme left and the extreme right boundaries of the area in terms of x. These are just kind of horizontal lines if you want to envisage them as that there. So let's go and so we're going to get the area by integrating from 0 up to 8 of the top curve minus the bottom curve. A line is a curve technically. Okay. So top minus bottom. So the top this time, I don't want to flick back. I think the top was a line in this case, and the second one was a parabola. There you go. It is. So the top y equals 2x. We get rid of y. Okay. And the bottom one, x will take with 6x. Okay. The brackets are important here. The 2x, it'll be fine. There's nothing in front of that. But that take away in front of the second bracket, that's technically now a -1. It's going to multiply the contents of that bracket there. So -1 times x squared is -x squared, and -1 times -6x is going to be +6x. So we've got that there. So just come down the line, So the similar terms here are the 2x, which is positive, and the 6x, which is positive. So ignore the x squared in the centre there. So it's 2x add 6x, 8x, take away x squared. There you go. Okay, but now let's simplify. We got rid of the brackets, we gathered like terms. So 8x, that's really 8x to the 1. So the integration process is telling you to add 1 to that power there. So that 8x to the 1 goes to 8x to the 2 divided by that power now of 2. And the second one, x to the 2 goes x to the 3 and take that 3 downstairs. So we're going to have 8x to the 2 all over 2, take away x to the 3 all over 3. So we've got that there. We've packaged it up in a little kind of rectangular box here, rectangular brackets. We've shifted our limits to the right hand side. It doesn't really matter, you can keep them on the left if you want. So what we're going to do here is copy and paste the contents of the bracket, 8x squared over 2, take away x cubed over 3. But I think, see that 8 over 2 term, I think 8 over 2 is 4, so I think we're going to simplify that. Yeah, I've just done that. So now I'm going to copy and paste that. So see that 4x squared, take away the x cubed over 3. I'm going to copy and paste that twice. I'm going to get rid of x. That's what I've done there. So hopefully you can see whatever was in the line above in the rectangular brackets, I've duplicated that, and you're always taking away. Always, always, always. If I was in a class, we could go back. I'd have more time. But since this is this online learning, if we get time, maybe later, we could talk about it. But really, folks, it's just a technique. So just please have faith in me. And that's the faith of mathematics. So what we're going to do now, see in the first kind of larger bracket, we're going to put in what's called the upper limit. So see the two numbers to the right hand side of the rectangular brackets. So the 8's on the top, it's going to go in the first big left hand bracket anywhere I had x. So I'm going to have 4 times 8 squared, take away 8 cubed over 3. So I've just inserted 8 there. That was my upper limit. And the second one, I'm going to put in my lower limit, which is a 0. So I'm going to put that in there. So now we're going to do the mathematics. So 4 times, so this is where you need your calculator. So that first one here, 4 times 8 squared. So 8 squared is 64. 4 times 64, what's that? 256. 8 cubed, what's that? 512. That's 512 over 3. So I'm going to have 256 take away 512 over 3. Don't worry, this will appear on the next page. And see the contents of that second large bracket? That's all going to come out as 0. Try it with your calculator if you don't believe me. So 256 take away 512 over 3. Take away the 0. I've just, for consistency, I've just kept that there, that 0. So the 256 take away 512 over 3. Your calculator will take to, I could convert 256. I could put that over 3 and make that as, that's 750 and 18, 768. 768 over 3 take away 512 over 3 is going to give me 256 over 3. Yep, it does indeed. That doesn't matter. 256 over 3. I don't think that will simplify nicely. It might give me a decimal, but you could write it as a mixed number, like 85 and a third. So that gives you an indication. What size is this number? It's 85 and a bit. I can recognise that. Or you might even want to decimalise it, but I think that's fine to there myself. So I'm quite happy with that. I know I might have went through this quite fast, but as I always say, you can rewind these little videos. What we're interested in here is a technique here, and so that's what you need to take on board. So I think I'm fine to there. Oh, and remember, the scenario was in error, so we're putting units squared. So we didn't have centimetres, inches, kilometres, miles or anything like that. So I've just put in units squared, as I say, for completeness. So, oh, we're not going to go there. No, we are going to go there. For us here, at this level, we're just usually going to keep the functions to one being linear and one being quadratic. Linear means a straight line, quadratic is an x squared thing. So in order to sort out which one you want to take away, on the left-hand side, if it's positive x squared, that will be the bottom part. Okay? And the line will be the top function. That's the way it happens. On the right-hand side, the x squared part, just because of negative, the nature of having a negative front of the x squared, it makes it kind of look like a hill or a peak. So it'll be that quadratic take will be that will be the top. That's not a little minus there. I'm confusing myself. So I think I'm going to leave it there and just let you go and practice your exercise. And if you've got any questions, then can you come back to me, folks? So thanks again for listening in there. Okay, right, bye for now.